All right, this is such a ghetto setup, but whatever. Okay, no one's counting. I'm on the floor of my room right now trying to figure out a way to do this video for you guys. So, problem number 1. I guess this will work. All right, number 1. C5H12 plus O2 produces CO2 and H2O. 5 C's, 12 H's. That gives you 16 O's. I put an 8 there to balance it. B is going to ask for the volume of carbon dioxide. Okay, since carbon dioxide is a gas, they want the liters there. We're going to have to use PV equals nRT. So V equals nRT over P. So sum N multiplied by 0.0821 multiplied by the temperature in Kelvin divided by the pressure in atmospheres. So they gave you the pressure in millimeters of mercury, 785. Okay, so that's how many millimeters 1 atmosphere of gas pushes up. It happens to be 760. Okay, you can get that online. Now this is N, but the problem gave you 2.5 grams of that. So this is where the stoichiometry comes into play. 2.5 grams of pentane, there's 72 grams per every 1 mole of pentane. And there's a 1 to 5 mole ratio. So 1 mole of pentane, 5 moles of CO2. This is going to be your N, which is going to go right in there. And the answer, eventually, when you do this, is going to be some liters of CO2, which you have in your key. Okay. Now, C is your a very simple problem, actually. It says that you have 243 joules every time you have 5 grams of pentane. But they want to know how many joules, kilojoules, sorry. How many kilojoules per every 1 mole of pentane? So all we have to do is convert those 5.0 grams to moles. So 72 grams per every 1 mole. And that's moles of pentane. Take this number and take 243 kilojoules and divide it by this number of moles. And you have your answer there. Okay. So that is problem number 1. Let's now move into ghetto whiteboard problem number 2. Okay. So ghetto whiteboard problem number 2, combustion of propane. All right, combustion central here. A C3H8 plus O2 goes to CO2 plus H2O. 3, 4, 5. Okay. Delta H is going to be equal to the sum of all the broken bonds, and that's the reactants, minus the sum of all the formed bonds. That's the products. And I guess up here we can rock a Lewis structure. 2, 3, 4, 5, 6, 7, 8. Ghetto plus 5O goes to 3 linear nonpolar CO2s plus 4 of these. Hollow. Okay, so up here we have 2 CC bonds. Each CC bond is 347 plus 1, 2, 3, 4, 5, 6, 7, 8. 8 CH bonds, and each CH bond is 413. Minus 3 times 2 of the CO bonds, which is 799, plus 4 times 2 of the OH bonds, which is 467. Okay, and that's going to give you some answer in kilojoules per mole. C. I'm going to disagree with that, and I'm going to speak the answer and write the equation. This is the sum of the broken minus the sum of the formed. So the large negative delta G, or H from the combustion of propane results from the large release of energy that occurs when the strong bonds of the products are formed. You're not going to get a large negative number unless the formed bonds have a greater bond energy from the formation of those than it took to break the reactants. Let's look at D, which is the energy diagram, and that's going to help us understand this. So large EA, we can think of the EA actually as this value. The amount of energy that went in to break it is really essentially this value right here. And this value is less than this value, and that's why this is a longer drop. So if this is, let's say, A, and this is B, notice here that A is less than B. You actually go down farther. And that's why you're left with surplus energy in this case, and that would be your delta H. Okay. Now this is 1. Let's go on to the second part of this. Okay. So we got oxygen, and we got this graph of bond energy versus bond length. And we know that oxygen looks like this, and they got a graph that looks like this. And they said, what would happen if you put fluorine in here? Well, you know the fluorine is weaker. So if this is the break energy, we know the fluorine's going to be higher on this, okay? Okay, just, there's only one bond. And bond, there's only one bond. And we know that oxygen is going to be shorter, so this is going to be longer. And if this is the bond length, we know that it's going to be more over here. So there's that connection here. So it would look like that. That's F2, and that guy is your O2. And B. Clearly explain the logic behind your drawing. Okay, so the FF is a single bond. OO is a double bond. So this is a weaker intramolecular force. Okay, so because it's weaker, it's also longer. Okay, thus it has a shorter break energy, this value, and a longer bond length. Hopefully that helps. Oh, ghetto.